So this is ECE 3710 Group 1. It's Tristan Stotesbery, Spencer Durrant, Matthew Hunsaker, and Brandon Chen. For our project, we decided to do Pac-Man. So Spencer will explain how this is going on right here.
Okay, so what we have here is Pac-Man can pretty much move freely around the map. We weren't able to get the walls implemented quite yet, but we were able to get him so that he can eat the food and even go through the ghost and lose a life. However, with our implementation, we have to center it perfectly in order for that to actually happen, so I'll try and demonstrate that. And so if you notice, the hearts at the bottom will go down each time I go through a ghost, and it'll even stop if we lose all of our lives. And so that will require a reset. And so as we reset this, I'll explain that we can also actually pause the game. And you can see that the start menu is still on the screen, and that's just because we weren't able to add the compatibility with that with the assembly code that we've written, but it is implemented in the hardware. And so now I've paused it, and I can also unpause it, and it'll start working again as well.
Cool. So here's the assembly code we have for that demo that you just saw. It's everything in here is just for the movement and the colliding with the objects and colliding with the ghosts and losing lives. We, like Spencer said, we had code written for moving within the maze, as well as having the ghosts have an AI so they could move around and chase the Pac-Man, and having code to be able to have a start menu and a pause menu. But we had a lot of small bugs within that assembly code, and we weren't able to finish getting that debugged in time. So we decided to just stick with this demo that we showed you.
Okay, and over here is a quick example of our finite state machine that our CPU is following. So we first start with the fetch stage, which will fetch the instruction, then I'll decode it in the next stage. And between each of these stages is a rising edge of a clock. And so you can see in state 2, it's an R-type instruction where it can execute and then write back to the register. And then state 3 will occur if it's a store instruction, and that will just quickly write back into memory for the store instruction. And if it's a load, then it'll require an extra state, but it'll begin to load the address into the memory in state 4, and the data will not be ready until the next state, which is state 5. At that point, the output memory is ready, and that will be outputted to the register. Unless it is actually a branch or a jump instruction, then it will transition to state 6, where it will move the program counter and then consequently go back to the fetch stage after that. And then down here, this is kind of the inner workings of the CPU itself, all of it put together. We have our program counter incrementing, and then our muxes all over the place. Here is our block RAM, and that's where we can store our programs, and it'll come out of the output of it. It'll be decoded, and then it'll go into the FSM and the instruction registers. And throughout this whole process, it can execute any of the instructions that we have, and we also implemented an assembler so that we can actually write the assembly instructions and then write it into hexadecimal format, and that will be stored into the memory and read by that.
So here's our hardware setup. We have the FPGA here, which has the CPU running on it. Connected to it is the Raspberry Pi with the script that controls the controller. It's connected with these wires here to the FPGA, and we have it set so that whatever button you press on the D-pad of the Xbox controller, it changes a register in the CPU. So pressing up gives you a 1, down is a 2, left is a 4, and right is an 8. And we just had that hard-coded so that you can read in the CPU in assembly code to know what button is being pressed. The way that works is it reads from a Python script running on the Raspberry Pi, and it changes the outputs of these wires, so the data is being transferred in parallel. So each wire here represents one of the different buttons being pressed, as well as a common ground for all of them.
And coming back to the VGA, we just felt that we should also add how we were able to do this. So Pac-Man and the ghost and all the walls were actually implemented as what we call glyphs, sometimes referred to as sprites. So these are all just 20 by 20 grids of pixel values, except for the menu that you see here as a 54 by 54 glyph grid. The way that we're able to do all these walls in this fashion is we created a separate grid, and we read this grid in a different way to determine if a wall should be printed at that location or not. And the displays of the walls and their locations don't depend on the assembly code themselves. However, as you can tell, Pac-Man does, and the ghosts are also just written to memory, but Pac-Man's memory locations are clearly being updated, as well as the lives are in the bottom right corner.
Cool, so that's our project. Thank you.